Good morning, everyone. Welcome to the second day of SIGCOMM'. I'm Noah Zilberman, I'm the session chair, and we are going to start today with an exciting session of machine learning for networks. Our first speaker is Hang Zhu. He is a final year PhD student at Johns Hopkins, and he is supervised by Professor Xin Jin. He's broadly interested in computer networks and distributed systems with a focus on programmable networks and machine learning for systems and networking. Would you like just to unmute yourself and show who you are before we start your presentation?
Hi, everyone.
So what we're going to do is we are going to stream this presentation, and then we are going to have the panel where Hang Zhu will be joined by his colleague Varun Gupta as well. So let's start. I hope you'll have a great session today.
Hello, everyone. I'm Hang Zhu from Johns Hopkins University. Today, I'm glad to present our work, Network Planning with Deep Reinforcement Learning. This is a joint work with people at Johns Hopkins University, Facebook, and Peking University. Large content service providers usually operate a global network. To meet the operational requirements, it's a critical step in dimensioning the backbone network. The network planning problem is extremely hard in practice. First, it's cross-layer. We need to make decisions in both the IP layer and the optical layer to form a network plan. Second, it's a multi-phased iterative process. The planning process is done over the short-term and long-term horizons respectively to generate short-term actionable signals for operational teams while allowing optimal long-term network evolution strategy. Third, it's failure aware. We need to ensure the reliability of the backbone network under different failure scenarios. Existing approach formulates the network planning problem as an integral linear programming ILP problem and feed it into some ILP solvers such as Gorby, Cplex. However, the ILP approach usually hits the limit of scalability in production scale problems. In such cases, people rely on heuristics to trade optimality for tractability. We list some of them here. First, topology decomposition means the topology is decomposed into several smaller subtopologies, and each subtopology is solved with ILP separately. Topology transformation aims to reduce the search space or the number of variables, such as enlarging the capacity unit that can be added. Failure selection means we only try to satisfy a subset of failure scenarios at a time, and add more failure scenarios until all the scenarios are added. All of these heuristics aim to prune the search space to make the problem tractable. It's a tedious, time-consuming iterative process, even for experts to find a good trade-off between the optimality of the solution and the tractability of the ILP problem. Our approach is revisiting this problem with a different take using deep reinforcement learning. Someone may ask why RL can help solve the network planning problem. As we know, a typical goal of RL is to train the RL agent to learn to take multiple actions in an environment to maximize the accumulated reward it receives. The environment provides the state as the input and the reward as a feedback. There are basically two characteristics that make network planning a good fit for RL. First, network planning can be viewed as a problem where multiple decisions are made on the IP and optical layers. And RL is designed to solve such a multi-decision making problem. Second, the RL agent explores the search space, and exploits the learned structure of the environment to optimize its policy. This is similar to how humans design heuristics to take advantage of the network planning program structure to solve the problem. The real appeal here is that the RL agent can automatically do this and relieves humans from the tremendous efforts of developing the heuristics. So we build our approach in Neuroplan with deep RL. The input of Neuroplan consists of 5 components. The RL agent only needs to encode the network topologies. The other 4, traffic demand, failure scenarios, reliability policy, and custom model, are handled by the plan evaluator. The RL agent interacts with the plan evaluator to learn to generate network plans that minimize the network cost while satisfying the traffic demand under the reliability policy. After the learning process is completed, the RL agent outputs an initial plan for the first stage, and at the second stage, the ILP solver finds the final plan in the pruned search space near the initial plan. We will discuss such hybrid approach later. There are mainly 3 challenges to adapt RL for network planning. Challenge 1, how to trade off between optimality and tractability. We can use the RL to find reasonably good solutions, but given the combinatorial nature of the problem, it's both unpredictable and time-consuming for the RL to find the optimal solution directly. So we use a 2-stage hybrid approach, which use ILP to only search the space near the RL solution after the RL process is terminated. We use the relax factor alpha to control the size of the space to explore by ILP. With a small alpha, the ILP solver may finish the second stage quickly, while a large alpha allows ILP to explore a larger space. So how to design the RL training process to generate a feasible plan in the first stage? This figure shows one trajectory during the training process. The plan evaluator will decide if the current topology satisfies all the operational requirements. If it is, or the agent has taken a maximum number of actions, then the current trajectory will be terminated. If not, the RL agent will intelligently select an IP link to augment its capacity. There are 2 optimizations we made in the training process. First, we only allow adding capacity in the action space. Compared to an action space which allows both adding and reducing, only allowing adding leads to a smaller action space and a stable and simple training process. Second, to train the agent effectively, we use the cost of newly added capacity as the intermediate reward for each step to generate dense rewards. Then challenge 3 is how the RL agent encodes the network topology. There are 3 factors that make it challenging: structure pattern, link features, and parallel links. First, the network topology is actually a graph. To capture its structure pattern, we leverage graph neural network, DNN, that performs message propagation between neighbor nodes. While GNNs are most mature for handling node features, here we care about link features, which is link capacity. What's more, there may be multiple parallel links between 2 nodes. To deal with this, we propose a domain-specific node link transformation. This example shows the input topology before transformation on the left and the output topology after transformation on the right. The node names show the corresponding relationship between nodes and the links. Then the capacity becomes node feature in the transformed topology. The two parallel links, BC1 and BC2, are mapped to two nodes in the transformed topology. The evaluation consists of the optimality, scalability, sensitivity analysis, and the implementation efficiency. The code is publicly available at this GitHub link. In this talk, we will include the optimality and the scalability. We compare Neuroplan and ILP on small-scale problems to evaluate the optimality of Neuroplan. We also report the results of Neuroplan's first stage. We vary the original capacities of our topology A to create multiple synthetic problems, including 0%, 25%, 50%, 75%, and no change. The problem is harder with the smaller original capacities. The causal results are normalized with the results of ILP on each topology. Comparing the red bars with the green bars, we see that Neuroplan produces near optimal solutions for small-scale problems. Neuroplan can overcome the scalability issue encountered by ILP. In this figure, we compare the results of first stage Neuroplan, ILP heuristic, and ILP for 5 topologies. ILP heuristic integrates hand-designed heuristics into ILP to trade optimality for tractability. For faithful comparison, we use the same heuristic setups used in the production network. The causal results are normalized to that of ILP heuristic on each topology. The crosses indicate that ILP fails to scale to large topologies. Neuroplan outperforms ILP heuristic on large topologies and avoids human efforts to tune the heuristics. To conclude, Neuroplan is a deep reinforcement learning-based approach to solve the network planning problem. It uses graph neural network and a domain-specific node link transformation to encode the network topologies, and leverages a two-stage hybrid approach to find the final solution. By doing so, it avoids human efforts to trade off between optimality and tractability in the current approach. That's all, and thanks for listening.
Okay, thank you very much for this talk. And we are also joined, if you can just unmute yourself and turn on your camera. We are also joined for this session of questions by Varun Gupta. Varun is also an author on the paper and is at Facebook and currently working on problems related to modeling and optimizing Facebook production backbone networks. So I'm going to start with a few questions that are on the Slack. There are already quite a lot of questions, but we are only limited to 5 minutes. So first question by Ajay, and he asked a few questions, so I'll ask just one of them. How does timescale of network planning influence the accuracy of the ILP and RL?
Yes, we do have some figures to show in our papers. We show the reward for each epoch versus the number of epochs. So please refer to our paper.
Okay. Second question by I'm sorry if I'm mispronouncing Aishwarya. So first of all, the topic is really interesting by combining RL with network topologies. Can this model be used to build network topologies satisfying the constraints in addition to optimizing the topology?
Maybe I can answer that. Yeah. So the answer is, I guess, yes. In some cases, we do that, especially for long-term planning, where we know less about the topology. So yes, we are doing that, and some of the details are in the paper.
Okay. let's go to the next question. We have time for at least another question. Question by the program. Great talk. Can your solution be tweaked to provide network topology as an output instead? Or to put it in a different way, can users specify the rest of the inputs, also node properties, link properties, cost model, and then the RL agent comes up with a close to optimal topology design?
Yes, I think the question is, can we build the topology from the scratch? I think the answer is yes. Given the IP link candidates, we can start to build the network topology from the starting capacity is set to be 0.
Okay, well, thank you. I think that we are running out of time for this talk, but we already have quite a few questions on the Slack. So all authors, if you can, please answer these questions later on the Slack. And thank you again. So while we are switching to the next speaker, if you can please unmute yourself and turn on your camera, Jane. So I would like to say that all the papers in the sessions are fully reproducible. They all got the reproducible badge. So well, very well done for all the authors. That's really good for our community. So our second speaker is Jane Yuan. Jane is a candidate at the Network System Laboratory at the University of Southern California. She's currently interested in 2 research topics. One is building flexible high-speed packet processing systems, and the second is automating protocol code generation from specifications. She's graduating next year, and she's on the job market. And Jane's going to tell us all about semi-automated protocol disambiguation and code generation.
Hi, everyone. I'd like to tell you about semi-automated protocol of disambiguation and code generation. It is a joint work with collaborators at USC and in Hungary. We have open sourced our code on the GitHub. Now let me begin. For decades, network protocols such as BGP, TCP/IP, ICMP, IGMP, BFD, etc. have been used in the network to achieve different goals. To describe each protocol's behavior, the networking community uses natural language to specify protocol details and publishes specifications, such as RCs. Different protocol implementers integrate these specifications over time to write implementations that make the internet work. Our expectation of what a specification can achieve is that it should be precise and clear enough about protocol implementation details so that multiple implementers can generate functionality equivalent code. However, this expectation is not realistic because natural language is inherently ambiguous. Different people could come up with multiple interpretations of the specification and therefore write multiple versions of code. So next, let me show you such an ambiguous sentence example. This is a sentence in the ICMP RFC. It says, the checksum is the 16-bit ones complement of the ones complement sum of the ICMP message starting with the ICMP type. At first glance, it might not be obvious why the sentence is ambiguous. However, when we focus on the last part of this sentence, it explicitly mentions the checksum starts with ICMP type, but it doesn't mention where the checksum computation should end. So how could this affect a person's interpretation? Here I show the ICMP header to help illustrate how we can at least come up with the 2 different interpretations. One is to checksum only the ICMP header part, and the other is to checksum both the header and the payload. As shown, the 2 different interpretations would lead to different protocol implementations. With this example, we notice that using an ambiguous specification to implement network protocol code that particularly runs in the internet might result in buggy implementations and security vulnerabilities. Previous approaches address the mentioned issues by developing protocol specification languages or adopting static and dynamic analysis of actual protocol implementations, or necessitating expensive and time-consuming software engineering processes, like interoperability bake-offs. However, none of these approaches has succeeded in fully addressing the issues. The current state of products is to use natural language specifications. Therefore, in our approach, we want to keep English specification as it is and apply natural language processing techniques on it to discover existence of ambiguities. To do so, we need to understand the semantics of a specification, which is commonly termed as the semantic parsing. And ultimately, we want to leverage the results from semantic parsing to generate low-level executable protocol code. Since semantic parsing is not perfect and may possibly never be perfect in the future, once ambiguous sentences are found, we will need to involve human efforts to edit those sentences. When a specification is unambiguous, executable protocol code can be automatically generated. In this work, we face a number of challenges. First, semantic parser only parses generic terms, but specifications could use domain-specific language such as checksum, once complement, etc. Second, semantic parsing is not perfect, and therefore multiple representations might be generated, but only a subset is valid. Finally, when we generate semantic representations, we need to convert them into correct executable code. In this work, we make the following corresponding contributions. First, we extend the generic semantic parser with domain-specific syntax and semantics. Next, we automate disambiguation of poor semantic representations with defined checking rules. Third, we compile semantic representations into executable code. So now let me introduce our work, SAGE. SAGE has three components that correspond to the contributions. Respectively, they are semantic parsing, disambiguation, and code generator components. A complete RFC parsing workflow will look like this. In addition to the already introduced three components, human will be involved in a loop. After the disambiguation phase, if more than one representation remains, it means we discover ambiguities, so we provide feedback to the user, and who is likely the specification author, to resolve ambiguity by rewriting the sentence. And if a sentence is unambiguous, SAGE will proceed to map the semantic representation to a code snippet. The code snippet will undergo unit tests to check if it performs any under-specified protocol behavior. Next, I want to introduce the main idea of each component, and the first one is semantic parsing component. We use the method called combinatory categorical grammar, abbreviated as CCG. A CCG parser takes in a textual sentence and turns it into a semantic representation called a logical form. A simple logical form is composed of a predicate with a number of arguments. At the high level, a CCG parsing of a sentence involves slicing a sentence into multiple entities. We define the syntax and semantics of each. The CCG parser generates logical forms by reading the predefined entity combination rules, which are expressed with lambda expressions. Then the resulting logical forms are then used to verify if a sentence is ambiguous. The key observation here is that a logical form is a unifying abstraction for disambiguation and code generation. Next, let me introduce how we leverage these logical forms to discover ambiguities. If the CCG parser uses something other than exactly one logical form, we call it a true ambiguity. An example of a zero logical form case is that a sentence is incomplete due to a missing subject in the sentence. And an example of more than one LF case is that a sentence uses imprecise language, such as using a terminology that can be interpreted as two different concepts. CCG parser has limitations and could generate additional logical forms that do not indicate the true ambiguity cases. Therefore, we defined 5 types of checking rules to eliminate these additional LFs. The 5 checking rules are type, argument, ordering, predicate ordering, distributivity, and associativity, respectively. For more detailed introduction of the 5 checking rules, please find them in our paper. After disambiguation, every sentence yields only one logical form as an unambiguous specification. Then we move on to the code generator. The code generator works as follows. It takes in a logical form and its contextual information and turns it into executable code. This example is simple and straightforward to map a logical form to an executable code, but this converting process can get far more complex than the example. We discuss more complex issues in code generation in the paper. Next, I want to introduce how we evaluate the whole. I will cover end-to-end disambiguation and exploring generality evaluation. In the end-to-end evaluation, we apply SAGE on ICMP RFC. We use generic Linux ping and traceroute on the sender side and use the packet formulation function to generate reply packets back to the sender. The tested ping and traceroute programs are able to process our automatically generated reply packets. In this experiment, we show the automatic generated code from an ambiguous specification is able to interoperate with human-coded programs. In disambiguation evaluation, I want to show how effective disambiguation checks are. We apply this experiment on multiple protocols. For each, we show the highest count, the lowest count, and the average count of generated logical forms and shows how the value goes down to 1 after all checks are complete. In ICMP experiments, after disambiguation phase, we discovered 5 true ambiguous sentences. And after unit test, we discovered another 6. SAGE is also applied on significant parts of RFCs in other protocols, including IGMP, NTP, and BFD. As mentioned in the earlier talk, to support semantic parsing on networking text, we need to extend the syntax and semantics from generic parser. On top of the base syntax and semantic sets, we build SAGE to apply on ICMP. We add additional semantics to support IGMP, NTP, and BFD. From this table, we give you an idea of how much additional human effort is involved in supporting new protocol in SAGE. When evaluating BFD, it requires relatively more human effort because it adds additional semantic parsing capabilities compared to other protocols. We also analyze the disambiguation results for each protocol in the paper. While SAGE takes a significant step toward automatic specification processing, much work remains. In an RFC, there are many components. SAGE is able to parse packet formats, pseudocode. There remains other components SAGE hasn't supported, such as state machine, communication pattern, and architecture. In addition to the mentioned limitations, there is still room for SAGE to improve the involved human effort, such as how to assist editing ambiguous sentences, to extend SAGE to support more protocols, and to generalize code generation approach. So let me summarize what SAGE achieves. First, we extend the existing semantic parsing method with domain-specific knowledge and automate the process of ambiguity discovery, disambiguation, and code generation. Next, SAGE-generated code can interoperate with off-the-shelf tools and discovers a number of previous missed ambiguities. And finally, SAGE can also disambiguate and generate code from significant sections of IGMP, NTP, and BFD protocols. And that's all. I'm happy to take questions.
Hey, thank you very much for this talk. And I must say that this paper is very much an out-of-the-box thinking and a very nice idea. I really like it. There are already a few questions on the Slack, and there's even a very lively discussion there. So I'll start with the first question there by Romain. Pushing the discussion a bit beyond SAGE, do you think we should still use natural language for RFCs? Maybe a more formal context-specific language can solve the ambiguity problem at source. What are your thoughts?
So Yeah, we agree that the like different languages can help, but because we consider the readability of the specification as a very significant factor, so that's why we think it's still easier to use natural language to express inside the specification.
And if we change the way that we write specifications, do you think it will take away the need to check for ambiguity?
If we change the way for the specification, how we use it, yeah, I think we can still find out some certain ways to discover ambiguities, but then that is not analyzing the natural language part, and we cannot utilize the existing natural language processing tools.
So to follow up on this question, there's a question by Ethan. First of all, Jane, great talk, very interesting work. Have you observed any changes in RFC writing style over time that impact how easy or hard it is to use SAGE?
So if if I understand correctly, is that asking how easy or hard to use SAGE, right?
So if you are looking at different RFCs that you've worked on, can you comment on the writing style of the RFC and if it affected the use of
yes, yes. So for that part, I want to mention, for example, the recent changes such as regulating that the writer should use some markdown languages to write the specification. That kind of stylish can definitely assist SAGE to process the specification better.
Okay, and if you had to think about the next protocol that can use SAGE, which RFC would you pick for your next protocol for ambiguity check?
Sure. So our target is definitely like a more interesting protocol, such as the state machine-like protocol that includes like TCP and some other different protocols like BGP. These kind of protocols are our main targets for the next work.
Okay. Well, thank you very much, and it would be great if you can also comment on the questions on the Slack.
Sure. Thank you.
Thank you, and good luck. And we'll move to our third speaker. Our third speaker, if you can turn on your camera, please, is Shijun Zhang. He's a fifth-year PhD student at UPenn, where he is co-advised by Vincent Liu and Buntao Lu. His research is centered around the clouds and data centers, involving both data processing systems and the network. And he's also on the job market, so please do turn to him if you are looking for great researchers. So he's going to tell us all about MimicNet, fast performance estimates for data center networks with machine learning.
Hi, everyone. Thank you for watching this talk. My name is Shijun Zhang, and today I'm going to present MimicNet, a system that provides fast performance estimation for data center networks with machine learning. This is John work with my co-authors Kevin, Charlie, Sheng, Zhao, and Vincent. Now, today's data center networks are massive. In aggregate, they can connect hundreds of thousands of machines and process hundreds of billions of packets per second. The most popular network architecture for these systems is a hierarchical structure where clusters of server racks are connected by a series of core or spin switches. In this architecture, clusters are often the unit of expansion, and a real data center can scale up to hundreds of clusters. Over the years, many have proposed the systems to improve the performance of data center networks, including several in this conference. Unfortunately, a consistent challenge in designing these systems is evaluating their behavior at scale. As an example, I'm willing to bet that few, if any of you, have the resources to build and maintain a test bed that is the same size as a real production data center. It is important to note that simulations were originally intended to address this issue. Compared to other evaluation methods, simulations can scale to arbitrary sizes. They can model arbitrary data center protocols. and they can be instrumented by the users in arbitrary ways without impacting the simulated system behavior. Unfortunately, for today's packet-level simulators, even simulating 1 minute of a data center with 128 clusters can easily take more than a month. Obvious workarounds don't work well. For instance, parallelization can often reduce performance, and while running multiple instances can increase throughput by a constant factor, it does not improve time to results. Even techniques like flow-level approximation are incomplete solutions as they are inaccurate and they provide a limited capacity for instrumentation. Our system, MimicNet, is a packet-level simulator that tackles the scalability problem. The key idea behind MimicNet is that when simulating a full data center, we only simulate one cluster using full fidelity packet-level simulation. Instead, most of the network is approximated with machine learning to make the whole simulation really fast. Clusters that are approximated are called mimics. MimicNet works as follows. The first step is to run a small-scale simulation, which consists of exactly 2 clusters. One of the clusters is instrumented to gather training data for constructing machine learning models. The second step is to train the models using the generated data to construct a cluster approximation. These models can be optionally hyper-tuned to improve the accuracy. Finally, the last step is to compose the large-scale simulation by replacing all clusters with mimics, except one cluster that generates full fidelity traffic and performs users' instrumentation. We call this cluster the observable cluster. Now, to see why MimicNet can substantially speed up network simulation, we can examine what happens to traffic that passes through a given mimic cluster. There are 3 such types of traffic: traffic to and from the observable cluster, traffic to and from other mimics, and traffic that's purely local to the cluster. The reason why MimicNet is fast is that it ends up approximating everything except the observable traffic. It does this using 2 distinct types of machine learning models. The first are internal models, which entirely replace the cluster's switches and links by predicting the effect of the cluster network, including any effects of intra-mimic packets. The second are feeder models, which interact with the internal models to emulate the effect of inter-mimic traffic without actually needing inter-mimic traffic. All of this results in an ON traffic reduction. As a preview of the resulting speedup, we find that MimicNet can finish simulating 60 seconds of a 128 cluster data center network in 1 hour, which is 2 orders of magnitude faster than the full simulation. Surprisingly, this is also 7 times faster than flow-level simulation because flow-level simulation still has to check offloads. MimicNet is able to achieve all of this using a few domain-specific assumptions. Specifically, it requires that the data center network uses a failure-free fact tree topology, that is, traffic patterns scale proportionally with network size, that congestion primarily happens on flying to destination, and the connections that are logically isolated within a single host. Our paper goes into much more detail about these restrictions, as well as how they might be relaxed. However, the key takeaway is that MimicNet is not suited for every data center architecture or configuration, but that it can still provide useful performance estimation for a very broad class of network proposals, as I will show shortly. Okay, so in the rest of this talk, I will go into more details about the MimicNet internal and feeder models and how they work. For internal models, there are 2 goals. For external traffic, we want to predict the effect of the cluster network on every packet. For example, when a packet is generated in this cluster, the internal models should check whether the packet is dropped in the cluster, and if not, it should predict when the packet leaves and what its contents are when it leaves. For internal traffic, we want to remove such traffic and instead simply account for the effects in the predictions for external traffic. We formulated this modeling problem as machine learning tasks. Specifically, we model packet latency as a regression task, and packet drops as well as other modifications like ECN bit prediction as the classification problem. When constructing any machine learning model, there are many important decisions to make: which features to use, which loss functions, and which model. MimicNet carefully selects each using domain-specific knowledge and requirements. As an example for feature selection, MimicNet has an additional requirement beyond typical machine learning tasks. Specifically, that the features selected must be scalable. Scalable features are features that remain meaningful regardless of network size. They're important because MimicNet trains models at a small scale, but uses them at large scales. For example, given an ingress packet into a cluster, a local destination rack identifier is a scalable feature because that information does not change as clusters are added. In contrast, the raw source IP is not scalable because when we add more clusters, we will see IP addresses that did not exist in the small scale simulation. You can see our paper for more details about modeling the internal traffic of a cluster. In the end, MimicNet can predict the effects of a network very accurately. For instance, these are the ground truth of a 1 second network trace of running TCP Neuroplan. Latency is on the left and drops are on the right. MimicNet predicts both effects accurately. Compared to the internal models, modeling intermimic traffic with feeder models presents its own challenge. First, the intermimic traffic does not exist in the two cluster simulation where we generate the training data. Further, such traffic varies across different network sizes as the number of mimics varies. At the same time, since intermimic traffic is not directly observed, we can be more relaxed in the modeling without sacrificing overall simulation accuracy. Given all of these, we have designed parameterized generative feeder models that use flow-level approximation techniques to predict packet arrivals. A feeder takes flow distribution and network size as input and generates packets that a MimicNet will feed into internal models. The paper has details about how feeders are trained and used. Composing these models together, we get an N-cluster simulation in which one cluster is observable and the other N-1 are mimics. Each consists of a pair of internal models and a feeder. A proportional number of call switches connect all clusters. Okay, now let's look at how MimicNet performs in terms of both simulation accuracy and speed. First, let's see the accuracy of MimicNet at predicting flow completion times for large-scale simulations using TCP Neuroplan and drop-tail queues. In addition to the ground truth from the full fidelity simulation and MimicNet, we compare two approximation baselines. The first is small-scale baseline, which assumes that the simulation results at small scale can directly apply to large scale. This is what people are forced to do today for large-scale network simulations. The second is flow-level baseline, for which we use SimGrid, a popular flow-level simulator. Here's the result. The x-axis shows the flow completion time, and the y-axis shows the fraction of flows. This blue CDF shows the ground truth of the FCT distribution. This gray CDF shows the result from the small scale baseline. And this yellow dashed CDF is from the flow level baseline. To compare these quantitatively, we use a metric called the Wasserstein distance. Lower means better estimation. We can see that both baselines are very different than the ground truth. On the other hand, MimicNet is significantly more accurate. Additionally, MimicNet achieves high accuracy in estimating tail FCTs, while the two baselines either underestimate or overestimate tail FCTs significantly. MimicNet can achieve the result almost 700x faster than full fidelity packet level simulation and 7x faster than flow level simulation. The paper has many more evaluation results, including some example use cases of MimicNet, where, for instance, we were able to accurately and quickly explore the configuration space of a large data center network to find the optimal setup for a particular workload and set of protocols. To summarize this talk, we first show that evaluating innovations for data center networks is increasingly intractable due to the size and complexities of the network. Our proposed system, MimicNet, provides fast performance estimates by replacing almost all simulated clusters with machine learning models. To achieve high accuracy in its modeling, MimicNet carefully models the intra-cluster and inter-cluster traffic using the domain knowledge of data center networks. Finally, we use different network protocols to stress the modeling in MimicNet in different ways, and the results show that our system achieves both high simulation accuracy and speed. MimicNet is now publicly available on GitHub, and we hope you can check it out and test it with your own protocols and architectures.
Thank you very much. Very nice talk and very interesting work. We have a few questions on the Slack. If you can just unmute yourself to answer. First question, an amazing talk, Shijen. Can you comment on the training data for the models? What scale or size of models were used and how did you collect the data?
Yeah, so the first step in the MimicNet workflow is to generate the training data. So specifically, we run 2 clusters simulation. And we use one of the clusters, we instrument one of the clusters to generate all the training data we need.
So how big is the model itself?
So we use, the models used in MimicNet are parameterizable. So you can use any machine learning model. So currently we use LSTM, which consists of 2 hidden layers, output layer, etc. It's not a very big model.
Okay, next question by Romain. Thanks for the interesting talk. I have a question about the training of your Mimic models. Do you train your models only once or do you retrain regularly? And if so, how often do you retrain?
Right, thanks for the question. If you look at the workflow of MimicNet, there are several steps for acquiring the machine learning models that will be used to construct mimics. If these steps do not change, then you don't need to retrain the model. However, if any of the steps change, then you do need to retrain the model.
So
yeah.
There is actually a follow-up to that. So if not, how do you know the traffic conditions have changed or didn't change over time?
In terms of the workload, or?
So do you have any way to see if it changes over time or not?
Right. I mean, our paper has details about what can change and what cannot change when you use the MimicNet. But in terms of the workload, we do assume that when you train the models, the workloads are already there. So the workloads will not change from small scale to large scale.
Next question by Brighton. Very cool work. Do you think MimicNet could be used to upscale observed data to facilitate testing on larger emulated networks?
Sorry, can you repeat the question?
Do you think that MimicNet could be used to upscale observed data to facilitate testing on larger emulated networks? So let's come back to this question later. Another question.
I can answer it on the Slack.
On the Slack, yeah. What type of scenarios do you handle? Prediction of topology changes, software upgrades, traffic pattern changes on performance, and how close are models derived using simulation to real world?
Right, so currently we assume that topology will not change. And we assume that we assume fat tree, right, which is hierarchical topology. Yeah. So apart from the restrictions we make on the MimicNet, I mean, any protocols can be simulated using MimicNet. For example, the congestion control, load balancing.
Okay. One last question from Aditya. Thanks for the excellent work. Given the limitations we identify in slide 7, do we need MimicNet? For the same limitations or assumptions, would simple mathematical analysis tools like TCP throughput model suffice?
Yeah, I mean, modeling the networks, right, using closed form modeling techniques is difficult, right? So as we show in the evaluation that a popular flow level simulation do not accurately model the network. So we do think that MimicNet will produce a more accurate result.
Okay, well, thank you very much. There are more questions on the slide, so it would be great if you can answer the questions there. So thank you very much. And we'll move to our last speaker of the session. So the last talk and the next speaker is not on the job market. So our next speaker is Michael Shapira. He is a professor of computer science at the Hebrew University, and he studies the interface of networking and machine learning. So Michael is going to tell us about verifying learning augmented systems.
Hi, my name is Michael Shapira, and I want to talk about our paper on verifying learning augmented systems. This is based on joint work with Tomer Eliyahu, Yasmin Kazak, and Guy Katz from the Hebrew University of Jerusalem. So traditionally, computer and network systems are handcrafted by domain-specific experts. But recently, we've seen many systems that were designed based on a different paradigm, namely employing deep reinforcement learning for network system design. And in different contexts, such DRL-based systems have been shown to outperform the state of the art. When we talk about reinforcement learning, we're talking about an agent interacting with its environment. The agent, say a system, at each point in time t, observes the state of the environment, st, and then takes an action at. After selecting an action, it learns in hindsight the implications for performance of selecting that action in the form of a reward RT. And the agent's goal is to learn a policy, where by policy I mean a mapping between states and actions, between observed states and selected actions, that maximizes the expectation of over the sum of discounted rewards. However, DRL comes at a cost. And the reason is that in DRL, we employ a deep neural network to realize the RL agent. And DNNs, deep neural networks, are very much a black box, meaning it's difficult to determine whether a DRL policy would satisfy even basic correctness and/or security requirements. Of course, one can test the system by supplying it with different inputs, observing the outputs, and trying to figure out whether some desired property holds or not. But as noted a while back, testing shows the presence, not the absence of bugs. Our goal, in contrast, is to provably guarantee that a learned policy always meets designer and user or user-specified requirements. Or alternatively, to identify concrete scenarios in which a certain requirement is violated. And you can think of this as the analog of traditional software acceptance tests. And this is also useful for determining when the RL agent is sufficiently trained, because we can say that we want the agent to at least learn some basic requirements, right? Or to at least satisfy some basic requirements before it's done training. So our work builds on recent progress on DNN verification. DNN verification is a mathematical approach for reasoning about the behavior of deep neural networks. And more specifically, DNN verification engines establish that a DNN's mapping from its inputs to its outputs satisfies certain properties. However, the issue is that this task is in general computationally hard, and scalability is a major concern for DNN verification schemes. And consequently, such schemes are typically limited to verifying simple local properties for fairly small DNNs. And this problem is even further aggravated when reasoning about deep reinforcement learning policies, because as opposed to traditional DNN verification, deep reinforcement learning pertains to sequential decision making, meaning we're not just talking about one invocation of the DNN, we're talking about repeated invocations of the DNN, where each invocation affects the inputs or potentially affects the inputs of subsequent for subsequent invocations of the DNN. And the reason is that the DNN's output translates to an action that might affect the environment state, which in turn might affect the input that the DNN will see next. Hence, to verify a deep reinforcement learning policy, it's not sufficient to simply apply an off-the-shelf DNN verification tool. So one of our key observations is that recent DRL network systems are prime candidates for formal verification. And the reason is that as opposed to other areas like, say, computer vision, the inputs to the DNN in these contexts often encodes domain-specific and semantically meaningful features. And this means that the DNN itself doesn't have to extract meaningful features from raw data, as in other contexts. And this facilitates two things. One is using fairly small DNNs, which, as I mentioned, is important for verification to succeed using today's mechanisms. And the second is the ability to formulate complex properties by leveraging the fact that the input already consists of meaningful features. So we leverage this to present a general verification strategy and a tool that realizes this general strategy called WIRL. Our strategy consists of two components. The first is, for a given system, defining the state graph for that system and how we can transition between different states, or which transitions between different system states are legitimate. And in the context of DRL, this means that we want to be able to talk about the ongoing interaction between the agent, represented by the DNN, and its environment, be it the user or, in the case of decentralized system, other components of the same system. And this is done in our framework by formulating states as combinations of the input to the DNN and the DNN's output, and formulating transitions between states as transitions that make sense in terms of changes to the input that reflect changes to the state of the environment that could be triggered by the DNN's actions. This, of course, differs across systems. The second component of our strategy is running a bounded model checking algorithm on the negation of the property that we want to verify. So we do this incrementally. We have an incremental bounded model checking algorithm that takes as input the DNN and the negation of the property that we want to verify. And what this algorithm does is it looks at longer and longer sequences of transitions in the state graph that we formulated, seeking a violation of the property, that is, trying to verify whether the negation of the property is satisfiable. If it's satisfiable, then we've identified a concrete violation. Otherwise, we increment K, seeking longer sequences of transitions that violate the desired property. We exemplify the usefulness of our general strategy and tool by examining 3 case studies in which deep reinforcement learning has been applied to classical networking challenges. The first is congestion control, and specifically the Aurora congestion controller. The second is adaptive bitrate selection in video streaming, and specifically the Pensive video streamer. And the third is compute resource allocation, and specifically the DeepRM resource manager. Now, I should note that our results pertain to deterministic variants of these systems, because this is what WIRL currently supports, and also to the activation functions in the DNN that are currently supported by today's DNN verification engines, namely ReLU. And to provide an illustration of the kinds of properties that WIRL is capable of verifying, let's zoom in on the Aurora congestion controller. The Aurora congestion controller takes as input bounded history of aggregated statistics about network behavior. Specifically, the latency gradient, the latency ratio, and the sending ratio, which intuitively capture the extent to which, by which network latency has increased or decreased, and how many packets haven't arrived at the receiver out of those sent. The Aurora takes these statistics, feeds them into a DNN, and then outputs a change to the sending rate. In Aurora, this change is continuous, but for our purpose, think of this as a discrete output. Either we increase the current sending rate, we maintain the current sending rate, or we decrease the current sending rate. And four natural properties are: property one, if network conditions are excellent, we would want the rate to eventually change. We wouldn't want to be stuck at a suboptimal sending rate. Property two is a stronger requirement. If network conditions are excellent, we would want the rate to eventually increase. We would want to take advantage of the fact that there's probably available bandwidth. Property three says that if network conditions are poor, we want to immediately decrease the sending rate. And property four says that if network conditions are poor, we want to eventually decrease the sending rate. That is, it's fine if we don't immediately decrease it, but eventually we have to decrease it. Now, this is a very high-level exposition of these properties, and you're referred to the paper for a detailed description. And what we were able to show using Aurora is that properties 1 and 4 hold for fairly long sequences of transitions, whereas properties 2 and 3 are violated even for very short sequences of transitions. Now, WIRL has several limitations. First, as I mentioned before, it's limited to deterministic policies. Second, it's constrained by the expressiveness of today's DNN verification engines. Naturally, as these evolve, we will also be able to take advantage of the enhanced expressiveness afforded by progress. And maybe most importantly, we are limited by K. As K gets larger and larger, as we seek longer and longer sequences of transitions that violate the desired property, the task of examining such sequences becomes more computationally complex. And this means that at some point we have to stop. At some point the tool times out. And this is why we weren't able to show this for any K in the previous example, but for K-long sequences with K being 10 or 11. And this is fixed in WIRL 2.0, which is follow-up work that facilitates scalable verification of safety and liveness properties for unbounded K, and also provides some visibility into the inner workings of DLL systems through a combination of various verification techniques. So to summarize, we presented what we believe is the first method for verifying properties for DRL systems. We exemplified the usefulness of our approach by examining 3 important and interesting case studies. And we leave the reader with many exciting directions for future research. Thank you very much.
Okay, Michael. Turn on your camera. Excellent.
Yeah, still here.
Yeah. So while we are waiting for questions to come in, I have a quick question for you. It seems like you picked networking-related use cases, but is WIRL limited to networking, or is it a general tool and you just picked networking use cases for the evaluation?
So it's not limited in the sense that you could, in principle, apply it to any system. We picked networking-related applications both because it's close to our hearts, but also because, as I mentioned in the talk, the ones we've seen so far, and I think that's not coincidental, have this nice property that the DNN has fairly low dimension because the inputs are meaningful features. And that means that this is within reach of existing verification technology. But systems of this flavor that belong to other areas could be analyzed using WIRL.
Okay. Next question by Sanjay. Network, is this something that's applicable beyond networking, or so somewhat repeating the same question, or are there particular properties of networking problems that makes the approach better suited?
Right. So
do you want to extend a bit more about the properties?
Yeah. So one thing that I think was meaningful here was again that unlike computer vision applications, in the systems we've seen for networking, you don't just feed raw data into the system, but there's domain-specific expertise that defines certain features that people have used as inputs. And that means that the DNN can be much smaller because it doesn't extract features to the extent that it does in other areas. Another thing that was helpful to us is that in a lot of these systems that we've observed, the input has a very specific form, which is a bounded history of observations. Meaning, as you progress in time, it's very easy to reason about how the input might change. Most of the coordinates will remain the same, but they will be shifted by one, and so on. That's another thing that we leveraged in some of our analysis.
Okay, thanks. Next question, Basagar. Can you comment on how well can extend to DRL agents that have much longer historical impact on the action, like long history lengths, recurrent networks, etc.? Or can you talk a little on how the results of formal verification can actually help debug or analyze how the property came to be violated in the training process?
Yeah. So in terms of longer histories, and the less structure you have, naturally the problem becomes more complex. And when there's no structure, that is, if you're not assuming anything about the input or the DNN dimension, then you're back at square one, meaning this is just the general DRL verification question where we know that things are extremely hard to scale. But I don't think that that it's coincidental that we've seen this kind of structure for networking systems that are based on DRL. And I think this might also be true in other systems areas. So I'm hopeful that that this will find applications beyond the ones we've seen. In terms of how the results help debug or analyze the properties, so there's two answers here. First, when a property is violated, we actually present a concrete violation. So that might give intuition for what went wrong and what should be added to the training. You would want to see such scenarios because this might be an indication that it hasn't experienced sufficiently many such scenarios to learn. Also, in the follow-up work, we are able to go a step forward and identify the inputs, a range of inputs for which the system might fail, which is also conducive.
Okay, well, thank you very much. We are just on time, and we are now going to take a very, very quick break. At 45 minutes past the hour, we are going to start the next session, which is the panel discussion, The Journey, Navigating Different Stages of One's Research Career. So thank you all for attending this session, and we'll be back shortly.